Hello, everybody. Hello, good morning. You can hear me? I guess we'll start. Hello, my name's Andy Whitham. I'm the Director of Process Development at Cygnet Texkimp. Hope you're all well this morning. I'm here today to talk to you about basically our journey to filament winding and what we've been doing for the last 2 years while we weren't allowed to play out. So I'll start with what is a Cygnet Texkimp. A Cygnet Texkimp is a machine builder. I've been working in the Manchester area in the United Kingdom for about the last 50 years. There's the obligatory shot of the manufacturing hall. As you can see, it's quite busy. It represents about half of our facility there at Manchester, the other half being filled with about 75 individuals, most of whom are engineers or have an engineering background. So what do? We have a range of products, starting with creels, which we've been doing for almost since day one. We obviously do filament winding. This is why I'm here today. We have wide web converting, which is basically anything that requires value adding to a sheet of material. Once you've got a sheet of material, you might wish to cut it up into small tapes, ideal for automatic tape placement or that sort of high precision applications. We have automation and handling to stitch it all together. If you have a factory full of people, then we can help to reduce that. Of course, we have been talking about decom a lot during this JEC. That's a fibre reclamation process, which we are working with. And my favourite, of course, is the special projects and development area that takes up a lot of my time, which is exciting. So when we come to build a machine and talk about this sort of thing, our primary focus is, and always will be, all about the fibre. It's right there at the bottom. That's fundamentally where we like to think that we set ourselves apart in terms of the fibre handling and the care of the product as we process it. Of course, that's great, but you need a reason to buy a new machine, and that's the other area I think we'd be proud of focusing on, which is adding value. What is it about this particular project that we can do that makes your machine better than your competition's? So, filament winding. We started this journey maybe 5 years ago with what's typical for Cygnet Texkimp. We start at the most difficult, the most out there process we can think of and walk back to what everybody else has been trying to do. So that starts off with the 3D winder, which I'll talk about more in a moment. We had the multi-axis winder, which we debuted here, the FW504, which we debuted here in 2019, believe it or not. We took a little bit of an aside into added value in filament winding by developing a very high tension filament winder. From there, we sort of moved into, well, if you want to make a lot of something, what would you do? And throughout all of that process, we've been looking at the materials development as well that allows you to really get the best out of a high-speed winding process. So, I'm fortunate enough to have in our innovation centre in Northwich, near Manchester, we have a 7-metre long, 7-axis filament winding cell. And here it is, some years ago now, with the multi-axis winder in its 3D winder form that is capable of winding very long parts, very big parts. It's a great photograph. I thought it was a good place to start. So what is 3D winding or multi-axis winding? It is fundamentally a rotary process around a static mandrel. So it's definitely filament winding. It's not braiding. Let's be clear about that. But it is a lot like filament winding. It is quite fast. It keeps the fibres flat. And there is some interlacement, which I'll come into in a moment. If you can follow the diagram, it's best to think of the whole process as 16 filament winders all operating at the same time. The aim of the game in our first iteration, the 3D winding, was to make a part similar to this. You can see the interlacement coming from the top right there and moving around the corner. That's the aim of the 3D winder, to make parts like this. So we started out, of course, making a duct. It's very, very straight, very, very big. That sort of definition rate is very high. Then we did some structural parts for automotive. A very long pipe, we'll call it, for a different application that was focused on toe preg manufacture. And another proof of concept, which was basically what's become known internally as the bendy pipe. And that was really just a proof of concept to show that you could actually make a part with 0 degrees fibre in there around a corner. Of course, most of those things, as you saw, were flat. So most of the inquiries we got were straight. Most of the inquiries we got were, this is very nice around the corners, but tell me again how much fibre you can put down. So we stopped with the robot, because you have to have a robot programmer, you have to have all the infrastructure in your company to deal with robots. And we said, well, what's a simpler machine going to look like if you want to make a lot of parts very quickly, or a lot of pipes very quickly? And you can see here that the top right again is more filament winding geometries which are available to us. Bottom right is the sort of interlaced braiding, winding hybrid affair. And the main picture there is a proof of concept in terms of keep the rings stationary, move the part through the rings, and you'll be able to continuously produce a pipe or rod or other composite part. Again, very high volume, as quick as you can. So what does that machine look like? Well, it's here at the JEC, not far, far away. It's a simpler machine, which gives you the obvious benefits, if you like, of a more structurally sound machine. You're not waving something around on the end of a robot arm. We already had a 250 kilo robot to play with, and when you put 100 kilos of material on that, you haven't really got very much else for anything else. So with an eye to bigger bobbins, higher rates and so on, you move to a straight machine, straight line machine, which is automatable, etc., etc. Here it is in action. There's a little bit of a tail here. This is the machine with all 16 bobbins on, which you will not be able to see here today. The reason for that is, as all good engineers, we made the machine in its final form, ready to take it to this show, only to find that it was so good at putting material onto a part that we were going to need an awful lot of parts very quickly. So at one point you're, hooray, one, and at the second moment there's a lot of 5-minute intervals in 3 days. So we took half of the bobbins off and put a speed controller on it. Alternatively, we'd have been here all week, right? So, because it's not braiding or filament winding, we have been working with the University of Manchester and the Northwest Composite Centre to do some benchmarking. The aim behind that is to really give people a feel for, well, what are the strengths and benefits. In summary, that is, if you have got an application where the strengths of braiding, as either the positives of braiding or what you want, then filament winding will be nearer that spectrum, nearer that end of the metric. If, for example, on the other hand, you have a process where filament winding really ticks your boxes, then multi-axis winding will be nearer that end of the spectrum. So it sits very closely in the middle. Whether it's one thing is better or the other thing is better, it's usually, as you'd expect for a low crimp part, sits in the middle between the two. Oh. So this is filament winding. Again, this is at our factory in Northwich, back at base. What I'm going to call conventional filament winding is literally anything with a rotating mandrel. So this is an example of it producing a glass fibre wound bobbin. Very early on, we got 2 tension control positions on the head of the robot, feeding fibre onto the winder. Of course, typical Texkimp, we started with the first filament winding cell we delivered to a customer, has got everything we can possibly think to add to it. So integrated software, 7-axis machine. It's of course going to be on a robot. It's of course going to have online resin mixing. It's going to have automated or semi-automatic material handling to remove the preform. Oh, and we'll make it 2 meters diameter while we're there. It was a fairly successful project. Learned a lot doing it. 2019, taking that large robotic cell and making it a little bit more accessible, we unveiled the FW504 here at JEC. That's the 500 millimeter diameter 4-axis filament winder, which we were quite proud of. That essentially was our normal filament winder. Normal. The other point to add here is I mentioned earlier about what would you do if you were a customer with a particular interest in something that was a little bit different. That brings me nicely on to our high tension filament winder, which was an aside. Somebody came to us with we would like to wind a part with very high tension. So we developed a machine for them that winds a part at very high tension, at up to 1,000 newtons per toe. Obviously, depends on the toe count. Turns out carbon fiber can be stretchy at those kind of tensions, and basically what we did was develop a high-speed tensile tester for carbon fiber. Worked very well. Moving on. We're also working with materials on the thermoplastic side with Heraeus and the HUM3 system, where this is currently set up in our innovation centre again. This is allowing us to do some testing, do some work with the HUM system, the Comfill co-mingled fibre, as well as tapes, to make a foray into the relatively new world of thermoplastic winding. Of course, Cygnet Texkimp also make thermoplastic tape producing machinery, so this goes hand in hand with that. Okay. So that brings me nicely on to the Ascend program, which we're involved with GKN in the UK, or it's being led by GKN in the UK, which allows us to take all of those things that we mentioned earlier and bring them together and focus on making a thing. In this case, the thing would be hydrogen tanks. You may see one or two around this show. The project has made us focus on a lot of the materials. As you can see there, we make machinery to make materials. Fundamentally, that's been one of the areas we've been working on for the last 10 years. But that's wet winding, so that's improving our knowledge, improving the knowledge of wet winding for running at speed. Getting involved in the manufacture of toe preg machinery, so that you can have controlled volume fractions on your final filament wound part. And of course, thermoplastics. We've done quite a lot in thermoplastics over the last 5-6 years. So we have an ability to make thermoplastic tapes. Well, then the question is, well, what will you do with them? So that brings us to that. If you're going to make anything at speed, of course, the immediate answer is, well, what does a high-speed filament winding cell look like? Well, that's our shot at it. This will have a section of it built at our factory for demonstration, for trials, for testing come the end of this year. But fundamentally, if you're going to do volume manufacture, you need to set out to do volume manufacture. So it's a filament winding machine that would have multiple spindles, tie on, tie off, splice on the fly, bobbins come in a very standard size, and so on. Won't read through the slide. We have, of course, a good history of industrial automation for Cygnet Texkimp. So from our side, putting that all together to make a cell that works as a factory to make a lot of parts is actually relatively simple. Once we've got the process to manufacture a lot of things, moving that around so that it creates a functioning factory is actually right in our ballpark. We've been doing this for a lot of years. So yeah, you can see the photos, robots and boxes. In addition, these are AGVs. If you're not familiar, that's an automatic guided vehicle that will take your parts around a factory. So if you've finished filament winding, it's been through curing, you might want then to move it to a packing and assembly or testing area. These are a couple of simple ones that I'm actually allowed to show you. The one on the top left there is essentially bobbin handling. People don't do well when having to deal with a couple of 1,050 kilo bobbins day in, day out. So the hazards are much reduced for the operator. Of course, as a result of that, they're also much reduced for the parts. So this is an area we are developing, both in terms of the software to allow it to communicate with your factory management system and so on. And it would be unfair to leave the stand here without mentioning the recycling of all these parts. And there's two reasons for this. Firstly, if you're going to sign up to making hundreds of thousands of anything, you probably ought to think about how we're going to get rid of hundreds of thousands of anything. Secondly, we are partnered with Longworth, working with the decom system for recovering long fibres from composite parts. When I say long fibres, I mean as wound. So the tank you see there was a demonstrator that we've done in the last few weeks that took a tank, reclaimed the fibre, we rewound the tank with the long strand fibre. So got a bobbin of fibre from an existing piece of equipment. I'm sure I've missed lots and lots of things. So if you've got any questions, now's the time to ask them. Thank you. I don't want to do next. Good.
Oh, good morning.
Good morning.
There's a lot of focus on natural fibers here at the fair.
Yeah.
Does that impose any complications when you do filament winding?
From our perspective, not really. And the reason I say not really is that we are quite familiar with having to deal with all kinds of fibers. So if it can be processed, i.e. our customer has an application that requires a natural fiber or has a resin system, joining system, whatever, that works with that, we can handle it. So from my perspective, it's relatively straightforward. There are worse fibers to deal with. And as a machinery builder, that's really all I care about is, can I handle this fiber sympathetically? So that answers the question.
Great to hear.
Hi, Andy.
Morning.
The bar chart, could you explain it a bit more, please?
Yeah, so on the work we've done with Manchester University, we have, when I said the work we've done, we supplied parts, Manchester University did the testing in fairness. There is a trade-off, obviously, between braiding, which has got a lot of impact resistance or impact tolerance, and filament winding less so. And we're talking 5s and 10% here in that system. So, for example, I'm trying to do this from memory, but if you have a braided part, for example, you might have more impact tolerance than you have for a filament wound part. Because of the interlacement you see with the multi-axis winder, you have your step towards the benefits of braiding whilst keeping the fibres flat. On the other hand, if you say, well, I want the maximum strength, well, filament winding is probably your go-to for that because it keeps the fibres flat, everything's more like a pre-bring. But it's not as damage tolerance, it doesn't like impact. Again, because of the pseudo-interlacement, I'll call it, the 3D winder steps more towards the strengths of the filament wind part in that respect, having a higher damage tolerance than filament winding, but not as much as braiding. So it's kind of it gets you a little bit more of the other whenever you're using a multi-axis winder.
Thank you.
I would recommend reading that paper though, because it's a better explanation than I just gave.
When you do the thermoplastic winding at high speed, how do you melt the polymer at that high speed?
Good question, isn't it? So we've been working with the Heraea system just recently, which is a high-intensity light. Speak to this gentleman for more details. The speed of that it's not as fast as the filament winding you'd see with the thermoset. There's no chemical reaction going on, of course, but that's how we've been doing it. So you basically apply a very high-intensity lump of energy to the point at which you're winding. That melts the polymer, welds it together, and away you go. Equally, we have things like preheat, again using the Heraeus infrared sort of subsystem, warm mandrels and so on. So it's keep everything warm, apply a hot or a high-intensity energy source at the point where the fibre meets the mandrel, and continue. It's essentially the same as standard filament winding.
Oh, thanks. This could be a long academic discussion, I think.
Yeah. Anything else? In that case, I shall bid you thank you very much.